Hey, this is Simple Machines. This is unit number 10, page number 9, Simple Machines. Alright, usually when I start off this unit, or this little piece of this unit, I usually have a board. And I have someone like Nate, or I have someone like Miles, big and strong, come forward and try to take a nail and with their bare hands jam it into the wood. And I'm going to try to do that myself. So here I am, I'm trying to take jam it right into the, and I can't get it very far. It's as far as I can possibly get it. I can't get it any further. So I'm like, oh my gosh, I can't take this nail and jam it into the wood. That's as far as I can possibly. Now I'm sure probably Nate and Miles can get a little bit further, but that's as far as I can possibly get it. And then I ask somebody like maybe like Big Stuff, or maybe someone like Rosie, and I say, hey, come up here and put this nail into this wood. And Nate and Miles, they weren't able to exert a big enough force to push it in. And so then I show, I have Big Stuff, or I have Rosie come up here, and then I give them a hammer. And with a hammer, no problem, they can exert the force needed to push the nail into the hammer. And I look at Nate and I look at Miles and I say, hey, you two can't even push the nail in here, but Big Stuff and Rosie, no problem. They can exert the force that's needed to push the nail into the wood. And so I ask them, well then, what is this thing we call hammer? What does it really do for us? What does it really do? Because we know, in actuality, we know the Big Stuff and Rosie, they can't exert the force needed to push the nail into the block. But so then, what does the force really do? All right, here's what the force really does for us. Here's what the hammer really does for us. It multiplies the force. It takes the force that we give it, and it makes it bigger. There's no way. You saw me. There was no way in the world I was going to be able to exert a force big enough to push the nail into the wood. There's no way I was going to be able to do that. However, if I grab a hammer, the hammer will take my force, multiply it, and then enable me to be able to push the nail into the hammer. So it multiplies the force. And that's what a simple machine does for us. Okay, in general, and I'll fill out some of these bullets here, or these blanks. Okay, a machine is this. It's a device that makes life easier. Can you imagine trying to build a home without a hammer? It'd be nearly impossible. Hammers make building things, much, much easier. And they do that by either multiplying the force, which we talked about, so it makes the force bigger, or sometimes it'll change the direction of the force. And sometimes by simply changing the direction, it makes life a little bit easier. Alright, so here's what it is. Machines don't multiply the energy or the work. We're still doing the same amount of work, okay, or the same amount of energy. It just takes the force and makes it bigger. It doesn't take the amount of energy and make it bigger, just the force. So if actually the amount of energy was multiplied, what law would be violated? Well, that would be the law of the conservation of energy. And if you remember from classroom discussion, we've never seen an example where the law of conservation of energy has been violated. If you do, you let me know, and I'll walk your briefcase to Stockholm, and we'll celebrate your Nobel Prize in Physics together. So then what do machines really do? They simply transfer. Okay, they transfer that energy. Okay, and what do we call a transfer of energy? We call that work. Alright, so they transfer the energy that you exert, and they deliver it to the machine. They take the energy that you give to the machine, and they give it to the object. Alright, let me see if I can make that make sense. So here's my hammer, here's the nail, okay, and the wood. Okay, so really, and then here's my hand. So really, when the nail goes into the wood, I don't really push the nail into the wood. It's really the hammer that pushes the nail into the wood. I push on the hammer, and the hammer pushes on the nail. So it's almost like this domino effect. Okay? So the hammer multiplies the force and exerts that bigger force onto the nail. So it goes me to hammer, hammer to nail. The energy transfer is the same. So if I do 5 joules to the hammer does 5 joules to the nail. It just takes that force and makes that force much, much larger. Alright, next one. Machines are give and take devices. They give, okay, by multiplying or changing the direction of the force. Okay, so they say, hey, we'll multiply that force for you. But it's a take. So there's a give and a take. I'll scratch your back as long as you scratch my back. So here's the take on this. They take by causing you to move a machine a larger distance. And I think the best way of trying to illustrate that is by actually taking the nail out of the wood. So we just put the nail into the wood, now we'll take it out of the wood. Alright, and I'm going to go ahead and try to do that on my own here. And so let's see here. I'll kind of move this around a little bit, see if this actually works. I might have to stand up. And there it is. I got the nail out. And I'm going to try to, when I touched that nail, it became a little warmer. Remember that. Became a little warmer. Alright, so I'm going to draw a picture real quick on the side over here. And I know you guys love my intricate drawings. And so here's the block of wood, here's the nail, and let's see if I can draw this hammer very well. So here's that. Oh my gosh, that's pretty darn good. Alright, so impress myself. Alright, so what do? We exert a force. I'll make up numbers. Like let's say I exert like a 4 Newton force. Alright. The force that's going to be lifted up on this nail, see, now remember, what do machines do? They multiply forces. So if I exert, this is me, so maybe I'll go like my force, like me, alright? So that's my force, and then the machine is going to push up on the nail. Notice, this arrow here is much larger than this arrow. And so when I do that, maybe this might be like 12 newtons. I'm totally making this up. So this would be the force of the, I got M for me, and how about I come back here? I'll do this. I'll do F, Fisk, and this will be M. All right. So force of Fisk, force of the machine. All right. Now let's see here. When I pull back on this handle moves a little bit. Now the nail doesn't move very far, but the handle does. So the distance that I push, I'll do DF. The distance that I push on the nail might be kind of small. Maybe, or I'm sorry, it would be much larger compared to the distance that the hammer pushes on the nail. So maybe the distance that I move it, I'm just making these up. Maybe like 3. I am totally now exaggerating this. 3 meters. I'm just trying to make my numbers work later on. And the nail might only move. So this is the machine. 1 meter. So notice, I have to move the machine much further distance than what the machine moves the nail. So yeah, it'll make my force larger, but I have to move it a further distance. Now notice, what's 3 times 4? Isn't that 12? And that's Newton meters. And 12 Newton meters, that's a joule. Notice over here, 12 times 1, that's 12 joules as well. Notice the amount of work that I do is the same as the amount of work that the machine does. All it does is the machine just transfers that energy. It just takes the energy that I give it and transfers it. So the energy doesn't change. It's the force that gets multiplied. It's the force that gets multiplied. All right, now we got a couple equations down here that usually are associated with machines, and so it's called the work input and the work output. The work input is the force that the machine does, and they call that the work input is the force that I do, the operator, and they call that the resistance, R for resistance, and the resistant distance. So the input that goes into the machine, that's the resistant force and the distant force. Over here, this is the output, And that's the force that the machine does. And the force that the machine does, uh-oh, I got those wrong, I think. Let's see, resistance and effort. I had this wrong. Fix this. This is the effort force, and that's the effort distance. So what you do, I'll put maybe like you here. Force that you do is effort. Like you exert, you push. Over here, this is the resistant force and the resistant distance. So this is the machine. Okay? And resistance. And usually, if this is a perfect or an ideal situation, this guy and this guy are going to be the same. Usually they're the same, if it's ideal. The only problem is, do you remember? What did I say about this guy here? Remember there was a little bit of warmth, thermal energy that was produced? So like usually, let's see, now this is if an ideal situation, but in real situations, there's going to be a little bit of thermal energy generated. So let's say that I put in that 12 joules that we talked about earlier. This is me. This is the work input. And then some of that energy is going to go to thermal, okay, to heat that up, maybe like 1 joule. And then the rest will be output. And that might be like 11 joules. Now notice that same at the beginning and same at the end. So the total energy is the same. It just now is transformed into 2 other forms. And then notice, I don't get as much out, okay, as I started with. Now the total is still the same, but this is not useful work, or this is unuseful. This thermal energy, I don't really want that. So the amount of energy I get out is not as useful. They call this a real machine. So a real machine is when the energy that I get out is not as much as the energy that I put in. Now the total is still the same, keep that in mind, but useful energy. This is a real machine. And actually, all machines are real. We've never been able to build a machine where all the energy that we put in comes out in terms of useful work. Something is going to be produced, like thermal energy, or like when I was pounding there, so maybe there might be some sound energy. Okay, so maybe a joule of sound energy. That would make this 10 then. So my total is still 12. So we've never built a machine where all of this is 0 and then this becomes 12. So whatever I put in, something's going to go into sound and thermal. And we call that a real machine. All right, let's go to the next page. And let's take what we just did, and we'll put that into some bullet points. So here we go. So this is an ideal machine. Ideal means everything you put in comes out. So a machine that transfers all of the energy it receives from the operator to the object with no transformation of energy to sound or thermal. Ideal machines do not exist. If you can make one, if you find one, you let me know. And I will carry your briefcase to Stockholm, and we will celebrate your Nobel Prize in physics together. They don't exist. We've never found one to date. We do have real machines. Real machine is a machine that transfers some of the energy it receives from the operator to the object, and some of the energy to other forms, such as sound and thermal. All right, the efficiency of an ideal machine is 100%. 100% of what you put in comes out. 12 in, 12 out. While the efficiency of a real machine is going to be less than 100%. We don't get everything out in terms of useful energy. We always lose some to sound and thermal. All right, we're going to make a transition. We're going to go to simple machines now. And I'm just going to give you a quick little thing here. A simple machine is this. It's a machine that transfers energy, which we call work. We know that a transfer of energy is work with one movement. Okay, one movement. And there are a total of, there's a total of 6 simple machines. 6 simple machines. I'm just going to It says word bank. In class, I would have you maybe like brainstorm it together, come up with the word bank, and then I'll have you try to figure out which is which. Here on the video, I'm just going to go ahead and give them to you. So the first one is called an inclined plane. That's I-N-C-L-I-N-E-D, inclined plane. It's a slanted surface used to raise an object, or more simply, it's a ramp. That's an inclined plane. Very simple. It's a ramp. Okay. Examples of these is a wheelchair ramp, a slide. Okay, that a kid would slide down. That would be an inclined plane. U-Haul ramps at the end of those big U-Haul trucks. You can pull out these big ramps. Here's this truck, right? All right, big long ramps that you can use to lift things with a little bit easier. Skateboard ramps. Those are all great examples of inclined planes. All right, a wedge. A wedge is simply an inclined plane that moves. Examples. A knife is an inclined plane that moves. An axe, inclined plane that moves. Your teeth are inclined planes. Are wedges. A doorstop, okay, is a wedge. All those are wedges. Next one. A screw. A screw is an inclined plane wrapped around a cylinder. Inclined plane. Let's see if I can do this very well. So here it is here. And there are threads. Okay. Some threads are real close, and some threads are real spread apart. These type of screws, the ones that have the threads really, really tight together, those are actually easier to use, easier to screw in than these guys. But it's basically a screw is an inclined plane wrapped around a cylinder. I think there was like a Big Bang Theory little episode about a screw there. If you can find that, I might give you some extra credit. The next one's a pulley. Okay, a pulley is a chain, belt, or rope wrapped around a wheel. Okay, so here it is here. So you're just trying to lift something generally with a pulley. The next one's a wheel and axle. Okay, gears. If you want some examples, gears in your engine or your car engine are wheels and axles. A water wheel is an axle. Ferris wheel is a wheel and axle. All right, and the last one is a lever. And a lever is a bar that's free to pivot or move about a free point. And the best example to instantly kind of understand this is a seesaw. Okay, so right, seesaw. Okay, teeter-totter. All right, and once we start talking about levers, there are three classes of levers. Three classes of levers. And the classes of levers all depends upon where the fulcrum is. And so I'll do the first one, then we can kind of talk about it. So when the fulcrum is in the middle, or someplace in the middle, okay, we call this a first class lever. So you might push down on this side. This is maybe your force, the effort force. And maybe that means like your friend sits over here, something you want to lift, and that would be the resistant force. So you push down, and the seesaw or the lever pushes up on the object. Examples of first class levers. Seesaws, pliers, okay, or scissors are examples of seesaws. A crowbar is an example of a seesaw, and if we get some time in class, I'll actually hold these up and we can kind of do a quick review in class, and that would be just fine. All right, second class lever. Second class lever is going to have your pivot point, the fulcrum, out on the left, and FE is actually in the middle. So you're going to push up from the middle. I lied. You're going to push up from the edge. Okay, so you're going to push out here, and this is going to be FR. So maybe you maybe have something over here that you want to lift, and so you pull up over here, and then the lever will push up. A great example of this is a wheelbarrow. Can you see the wheelbarrow? Here's the wheel sitting out here, and you're trying to lift something, and you're pushing up. So this is a great second class lever. Another example is a door paper cutters. Remember those paper cutters in the office? You like, right? You grab it and whoom, whoom. Okay, pivot points down here. You're pushing over here, and then the knife blade is in the middle. Okay, so there's the FR. Shoom. That's a great one. Nutcrackers are other examples of second-class levers. And then the last one, third class. Okay, fulcrum is going to sit out here. This is where you push up over here. So this is going to be FE. You push up here, and what you're trying to lift usually is over here, and that's going to be like FR. Examples of this. Your arm is a third-class lever. I'll kind of explain that in just a moment on our next example. Let's see here. You're a bat. This is going to confuse Cub fans. I'm sorry, Cub fans. I didn't mean to confuse you when I wrote that down. So like a baseball bat. So if we need to kind of help you guys out with that, we can help you out with that a little bit later on. I'm going to do the arm here on this next example. Let's turn the page. So here's an example. Example number 4. In our bodies, torques are produced by the contraction of our muscles that cause some bones to rotate at joints. For example, when you lift something with your forearm, a torque is applied on the lower arm by the bicep muscle. With the axis of rotation through the elbow joint, so here's your elbow, okay, right down there. Here's the muscle, your bicep, okay, attached, and there's a little bitty like distance here, and I don't know if I can hold my arm up, but here's my elbow. I got a little scratch there running on the trails one day. So here's my elbow, and my bicep muscle comes down. My bulging bicep muscle, right? Okay, so here it is. Here's my elbow, and you can do this on yours. My bicep is up here, and if you flex a little bit, you'll feel a tendon right here. It's actually kind of feels weird to actually feel it. That tendon goes down and connects down here, not actually on your elbow, but a little bit in, and this is about 4 centimeters right in here. So your muscle actually pulls on your bone, okay, about 4 centimeters from the joint, which is your pivot point right over here, and it lifts your forearm. Alright, so what we want to do is we want to figure out the torque that's exerted by that. And so we'll go back to the torque equation, and we know torque is going to be R cross F, and so here's RF sine theta, and then R, this is the 4 meters that was listed, or 4 centimeters that was listed earlier, so here's this guy, and then F is 600 newtons, that's listed in the problem, and here's our sine. Now check this out. Here's the angle. It's 90 degrees between them, so we'll go 90, and if I multiply those through very simply, okay, I'll get 24 meter newtons, and I'm only looking for the magnitude of it, so I'm not worried about the right hand rule when we do this one. So 24 meter newtons. Alright, now let's slide over. What happens when your arm is stretched out a little bit more? So here's RF sine theta. Okay, we still have this 4 centimeters, so that's still there. So 4 centimeters, that'll be 0.04 meters. And then here's your force. It's still your bicep is still exerting the same amount of force, but the angle is going to change. In this case, the angle now is going to be a 30-degree angle sitting inside of there. So I'll put in the 30 there, and I'll let you go ahead and multiply it through on your calculator. And alright, if I do 30 in there, so I'll do mine. Sorry about being a little slow here. Get my calculator warmed up. Alright, so this is 0.04 times 600 times sine of 30, and I get 12 meter newtons. So notice, where are you going to have the most torque? You're going to have the most torque when you're at 90 degrees over here, because this is 24 while this is only 12. And so you get more torque at 90 than you do at this one. So then how would the graph of the torque look like as the arm is raised and then lowered? Well, at the beginning, you know, the torque is going to be 24. It's going to be kind of like at maximum, maybe like 24. And then as you lower your arm, right, it's going to go probably down to 0, Okay, maybe it's when it's all the way extended, so you get very little to no torque, right? And then maybe come back up, and as you raise your arm up and down, you almost get like a sine curve that's been shifted a little bit. All right, the last one, and then we're done, is to classify this lever. Well, check this out. If I go up here, here's the fulcrum, right? Here's my force. This is the effort force, and what I'm trying to lift sits out here. So this is FR. So when FE is in between the fulcrum and FR, we classify this guy as a second class lever. And that's how God designed you and me. That's it. Have a great day.